Welcome to the page 4 video tutorial for thermochemistry homework, and we're going to get started right up here. What I want to do first is draw a little illustration to help us figure out the phase changes, and I am actually going to draw this right here at the top. And when we're starting with our phase changes, we're going to think about solids. They're our most tightly packed together, right? So let's just say we're talking about ice, because we're all familiar with water and ice and steam. So we'll just say this is a solid. I'll put in parentheses ice, so we know we're talking about ice. Very tightly packed together. Then if we melt our ice, so we can say melting, we do that by adding a little bit of energy. So going this direction, going from left to right, we're going to say we're adding in some energy into our system. So we're going to put that in there, add that energy in there, and then we're going to melt this ice, and of course we're going to make some water. The molecules here are less tightly packed. Of course, we know water, being more accurate, would look like this, right? H2O. But I'm just going to draw it like this for simplicity's sake. Now, what happens if we heat that even further, add a little more energy in the form of heat? So add more energy. You are, of course, going to get some steam or water vapor. So what will happen is that there'll be some evaporation. So the liquid water will evaporate into some steam, and you're going to end up with some molecules that are very far apart and kind of bouncing around. Draw these little lines to indicate that they're moving around really fast. But if we go the opposite direction, we have to remove some energy. So if we go this way, we're going to take energy away. So over here we wrote add energy. Now we're going to go this way, and you can say, now let's see what happens when we remove energy. Okay, so I want to take away some of my energy. I'm going to take away some of my energy, and so I'm going to go from steam, or the gas state, right, our water vapor, and the water will condense a little bit. So this is condense, and we'll go back to from water vapor to liquid water. And then if we remove even more energy, you're going to go from water, like solid, just regular water, to ice, back to ice. And of course this is called freezing. So we can see now more clearly the steps that require the addition of energy. Okay, so when we're melting, evaporating, that requires putting some energy into the system. And if we go the other way, if we condense or freeze, we have to take that energy away. So hopefully that will make this next part a little easier to understand. If you stuck with me there, we're going to say +4 for drawing all that out. Good work there. That was a lot of drawing. So that will take us to this next section. Okay, so this says solid, and you're going to a liquid. Okay, so we're going from a solid to a liquid. So this is, we can find it, what it happens when you go from solid, let's think about ice, to liquid water. We can see this right in that drawing we made. Solid to liquid, that is melting. And melting is an endothermic process. Okay, that means we have to add energy. Endo, my little memory trick for endo is saying into, because they both have 4 letters. So endo, into. Exo, I like to think of exit, because the energy exits. You have to take it out. So melting, we have to add energy. We have to put energy into the system. So that is an endothermic reaction. All right, so how about if we go from liquid to gas? Click on this next one. Okay, so from liquid, here we are in the liquid state, the water, to gas. That is going to be, from liquid to gas, we're going to be boiling. I didn't label that in there, but this is boiling. So when we add that energy there, that's boiling, or evaporating, right? These are both the same kind of process, right? You boil your water and you're going to get that water to evaporate. So that is also endothermic. Hold on. Let me pause this. Okay, sorry about that. Quick little interruption, but we're going to keep going. So this is, we were on endothermic, and let's continue. So our next one is solid to gas. Alright, so here, solid to gas. Actually, you know what? I'm going to do this one. Gas to solid. Let's do gas to solid so we can have a little bit more variety. So from gas, this is our gas state up here, the gas, the most energetic. And we want to get, gas to liquid. So we're going to have to remove energy to go from gas to the liquid state. That is removing energy. So that energy is going to exit. So remember, exothermic, exiting. You want to think about the word exit. The energy is going to go out of the system. It's going to exit the system. So this is exothermic. And the name of that change from when you are going from a gas to a liquid is called condensing. And let's try from gas to a solid, because that's a little bit more of a strange situation. We don't see this a lot in Houston, but I can tell you one example of this is snow. So when we go from water vapor up in the clouds down to solid snow, we don't see this a lot in Houston, but that is called deposition. But once again, it's just skipping this step here of liquid, but you can see again it's removing energy. So that is exothermic, because the energy is going to exit. Exothermic. All right. So let's continue on. Has the highest kinetic energy. So we can see our little picture up there, our gas jumping around. They are very energetic, those gas molecules. So that is a gas. Produced after sublimation. So sublimation is another one of those strange ones. What I like to think of for sublimation is dry ice. So for dry ice, the reason it is called dry is because you're not left over with a little puddle afterwards. You just go from a solid block of ice to, of course, some water vapor. So what is produced after sublimation? That is going to be, or not water vapor, I guess it would be nitrogen. It's gas. Produced after sublimation is gas, because you're going from the solid just to the gas state. So that is a G for gas. We could write it. Okay, shape will not change. That would be a solid. Solids do not change shape. Right. And let's do has the least entropy, so the least amount of disorder. That would be a solid again. They're very orderly. And this should also answer K for you, has the least disorder, because entropy and disorder are kind of the same thing. Entropy is just a measure of disorder and randomness. Gases are, of course, very disordered, but solids are quite orderly. Shape changes, and volume doesn't. Shape changes, but the volume won't. That will be a liquid. So if I measure out, if you think about milk cartons, that's a good example, because some milks are more of the rectangular and some of them are the more circular. But if it's half a gallon, it doesn't matter what shape you get, right? It's still half a gallon. The volume won't change. Completely fills a container. That would be gas. Gas will take the shape of its container. Okay. So place the states of matter in order from most decreasing order. We're placing them in decreasing order from most disordered. So most disordered, most entropy to least. The most disordered is gas, followed by liquid, followed by solid, and it kind of goes back to our shapes. That's the most disordered. This is a little more ordered. This is the most orderly. In comparison with liquids and solids, gases generally, here are our choices, have more entropy. Again, entropy means disorder. That is true. Gases are very disordered. So there we go. So here you go. Disorder. Entropy. More or less. Now don't get mad at me when you're in advanced physics in college, but we'll go ahead and say +1 there. Disorder / randomness. That is what entropy is at a most basic level. Okay, so let's see. I'm going to do this one, even though I didn't circle it before. In order for an ice cube to melt energy, what is going to be happening with our energy there? So let's think about what happens when we're going to go up to the thing we drew again. Okay, so we have ice cube going from a solid, coming from very ordered, to liquid, right? So melting. That means we have to put energy into the system. Okay, so if energy is going into, that is an endothermic, right? So we have to do something. So neither of these is going to be correct, not B or D. So do we want to think about absorb or release? So if we're putting energy into it, it's going to be absorbed. We're going to put energy into the system. We're going to not release, because that would melt it, right? That would mean we were removing it. So in order for an ice cube to melt, energy needs to be absorbed. And one more question. An endothermic reaction, blank to the surroundings. So we've got, again, our choices: releases heat, creates heat, absorbs heat, destroys heat. Okay, so we can't create heat because we have to follow the law of conservation of energy. So we can't create or destroy. So we can eliminate two answers. So we're thinking about endothermic. So we have to put into. Okay, we're going to put heat into the system. Just like this question above, we're putting it into the system. So we're absorbing it. And now that's going to be it for this page, and we'll see you in the next video.